we're going to make use of these data that you've seen before. These are data from a in-class IE361 class exercise. I'm not going to, in this module, use the ranges or the range-based calculations, but these basic measurements here we are going to use. So this is a situation where we have 4 parts. So this is a context where I is 4, J, there are 3 operators, so there are 3 operators, J is equal to 3, and each operator makes 2 measurements on each of the parts. So there are those sample sizes, if you will, involved in this study. We are going to use statistical software, that is JUMP, to cook up, or to essentially cook up, what is called a two-way analysis of variance table. And so let me show you in generic terms what a two-way ANOVA table looks like. This table is a summary of a two-way data set like the gauge R&R data sets that we're working with, that has rows and columns, obviously, and the columns are named source, a sum of squares, degrees of freedom, and a mean square source. And it has rows that are named by part, by operator, part times operator, or interaction of part with operator, error, and then a total. These sources I'm going to call part source A. Operator, it would be natural to call it source B, but in order to avoid notational conflict with the idea of a bias, B, decided we'll call operator source C. Part by operator, or operator by part, we'll call source A by C. And in this table there are entries that are essentially various kinds of sample variances. And a sample variance that pretty much ignores rows and columns gives rise to what people call a total sum of squares. A sample variance that is sort of a sample variance of row averages gets called a part sum of squares. A sample variance that is essentially a sample variance of operator averages gets called SSC. If one takes sample variances within cells and sort of pools them together in a sensible kind of way, one gets what would be called an error sum of squares, and what's left over from that total gets called a sum of squares for interaction, sum of squares AC. In this table, the degrees of freedom column gets filled in by number of parts minus 1, number of operators minus 1. This entry down here is number of cells times the sample size within a cell minus 1. This entry is total number of measurements minus 1, and so things add up. Turns out that you want the product of I minus 1 and J minus 1 there. And the raw material for our gauge R&R calculations is going to be what gets put in this table in these three places. And what gets put in the table in those three places are ratios of sums of squares to degrees of freedom. So there's going to be a mean square for operators, or a mean square for C, that is a sum of squares for C over J minus 1. There will be a mean square for error that is a sum of squares for error over I, J times M minus 1. And there will be a sum of squares for part by operator interaction, a mean square for part by operator interaction, so that'll be a mean square for AC that is the ratio of a sum of squares for AC over this I minus 1, J minus 1. Now, truth be told, I've been saying to you that the sum of squares column is a kind of, or has in it a kind of sample variances. It's really the mean square column that is closer to sample variances in its interpretation, but the mean square values are just multiples off of, you take the sum of squares, you divide by quote-unquote degrees of freedom. It is this, and this that we are going to use to make confidence intervals for sigma repeatability, sigma reproducibility, and sigma R&R. There are hand formulas. Nobody in the world does ANOVA calculations by hand. So I'm not even going to show you the hand formulas. If you want to see them, you need to go find yourself sort of an intermediate level statistical methods book. Rather than show you the hand formulas, what I'm going to do is show you how to use statistical software to compute these things. And then we will simply take these numbers as inputs to gauge R&R calculations. So let me show you how one gets entries to this analysis of variance table from a jump run. So here is the data set that we used in Module 5 and we'll use in this module as well in jump data table form. If I want then to quickly get the mean squares that are necessary in order to use the formulas for this module, what I'm going to do is come to this Analyze menu, use Fit Model. You'll notice that in this setup, I've made part a nominal variable. I've made operator a nominal variable. The peanut measurement is, of course, a continuous variable. And the peanut measurement is going to be my response. So it goes in this part of the dialog box as a y. Part is one of my explanatory variables. It goes down here in the construct model effects part of this dialog box, as does operator. And now I need to include not just part operator, but a part by operator so-called interaction effect in my analysis. So I highlight part over here, operator over here, and I hit the cross button, and I get an operator by part interaction. I, of course, can do that in the other way. I could have highlighted operator on the left, part on the right. It would have just changed the name here to part by operator. It would not have made a difference in what's actually going to get printed out for a calculation. I tell jump to go, and it produces way more stuff than I want to really talk about here. Let me close most of this, and let's just look at the parts of this printout that are of fundamental interest to me in this particular context. There is an analysis of variance table here. It's not as extensive or as expanded as the generic one that I just showed you. And I'm going to be able to get only part of what I need from this table. I'm going to have to use it and the effects test table to finally get everything that I want for this analysis. What I want to point out to you is that in this analysis of variance table, there is an error line, and there is a mean square column. Sitting there on the error line and the mean square column in this jump report is a mean square for error, this 0.4029. That's the thing that I've called MSE in the generic table. So that's one item that I'm going to want from this table. If I come down here to this effects test business, there is no mean square column in this effects test part of the jump report, but there is a sum of squares column, and there's a degrees of freedom column. And so this entry 000080833, that operator sum of squares, is the thing that I have called SSC. That's the operator sum of squares. If I copy that down from this table, I divide by degrees of freedom. Degrees of freedom, j minus 1, 3 operators minus 1 is 2. If I divide the sum of squares by the degrees of freedom, I get the mean square for operator, MSC, that I need for my calculations in this gauge R&R scenario. Similarly, there is this number 000725 that is a part by operator, or operator by part, either way you want to think about it, sum of squares. That's the thing that I would call SSAC, it has associated degrees of freedom 6. 6 is number of parts minus 1, i.e. 3, times number of operators minus 1, that is 2. 3 by 2 is 6. If I take the ratio of the sum of squares to that degrees of freedom, I will get a mean square for AC that I'm going to enter into my gauge R&R formulas. Okay, so it's just an artifact of the way that JMP is set up that I cannot read out all of my mean squares from the same table. It's not a big deal. From the quote-unquote analysis of variance table in the JMP report, I read the mean square for error. I have to go down to this quote-unquote effects test and get sum of squares and degrees of freedom for operator, that is factor C, and operator by part, that is the interaction of factors A and C, read out sum of squares and degrees of freedom, and compute a mean square offline. Okay, so that's where I'm going to get those three numbers that I have highlighted on this page of our lecture here, of our notes.